Good morning, distinguished visitors, ladies and gentlemen. It's a great honor to introduce the first speaker of this workshop, who has been a good friend of mine for, I guess, well over 20 years, and has had a great influence on my own research work. He's also not a stranger to the University of Tampere, since, as has been mentioned, this is the third in a series of either seminars, conferences, or workshops that have been held here from 1983 and then in 1987 and now in 1990. Professor Kalyanpudi Radhakrishna Rao is the Eberly Professor of Statistics at Pennsylvania State University in University Park, Pennsylvania, and the National Professor of India. Professor Rao was at one time the director of the Indian Statistical Institute in Calcutta and I guess in Delhi, where I had the privilege of visiting him. Among recent accolades that have been accorded to him is an honorary PhD from the University of Tampere, and I asked him how many more of such honorary PhDs he had, and he put out the 10 fingers of his hand. I wonder what he will do when he gets the 11th honorary PhD, which digit he will show us. His talk today is on uncertainty, statistics, and the creation of new knowledge. Professor Rao.
I would like to thank the organizers for inviting me to give a talk at the opening session. Now, each of the terms in the title, uncertainty, statistics, and creation of new knowledge, is worthy to be the subject of a lengthy discourse. During the short time allotted to me, I shall briefly indicate how statistics constitute the separating uncertainty from creation of new knowledge. This is implied in the title of my talk. The reason why I chose the title as in three terms. From times immemorial, mankind has been taking decisions under uncertainty. They have been learning from experience. They have also been building theories to explain observed natural phenomena. But no attempt has been made to codify the reasoning behind these intellectual exercises by which new knowledge is created. Often, new discoveries and the wise decisions we make are shrouded in mysticism or explained by chance or serendipity. Why did it take such a long time for the human mind to tackle problems of uncertainty? The reason may be that the human mind is essentially tuned to deductive logic of arguing from certainty or deriving consequences from given premises or axioms, which were introduced by the Greeks 2,000 years ago and perfected through the study of mathematics over the last several centuries. The given premises constitute the full knowledge, and the derived consequences cannot go wrong if our arguments are correct. But in the reverse process of creating knowledge from particular consequences, things can go wrong. Whatever rule we have prescribed for this purpose of creating knowledge from uncertainty, we can be wrong by following them. The human mind might have thought, how can there be a theory of inference by following which we cannot always be correct? The task was left to the philosophers who argued over the last several centuries, but they brought forth nothing useful. And a breakthrough occurred about the middle of the last century when attempts were made to describe rather than explain uncertainty. With this, the new subject of statistics was born, which began to be developed systematically from the beginning of the present century. Now let us look at the successes we have achieved during the last half a century. I begin with the concept of uncertainty. Now here are situations where uncertainty arises in a natural way. We may have lack of information because of the limitation of resources. We may not be able to collect all the information needed for taking a decision or for explaining a phenomenon. Now, even if we have resources, every piece of information we would like to acquire would involve certain measurements. Now, we will not be able to obtain precise measurements which we want. That is indicated by the modern equation that message is signal plus noise. Signal is what we are looking for, but it's always contaminated with noise. I must also add that sometimes information is faked, but that is misinformation. But in some sense, misinformation is also information. We may lack the technology for taking certain measurements, although we can define certain measurements, but we may not be able to find out what the value of the measurement is. There are, of course, situations where we are not able to take any measurement, so the nature hides information from us. So there's some amount of uncertainty arising out of that. Now finally, there's also lack of knowledge on optimum utilization of information. So these are the various ways in which uncertainty can arise in the problems we have to deal with. Now for a long time people believed that the universe is governed by, and if we know the state of a system at one point of time, we should be able to predict the state of the system at any future point of time. The proponent of this concept is Laplace. Now he introduced the what is called a mathematical demon, which is able to make the computations for us. But Laplace proved to be wrong in two ways. First, there are logical difficulties in forming deterministic laws for natural phenomena. And secondly, it's impossible to get the initial measurements of a system precisely. For instance, if we want to make a future weather prediction at a future point of time, now we need to know the certain initial measurements of the system. Now here is a graph which shows that even if there is a small difference in the initial measurement, 0.506217, instead of that, if you take it as 0.506, there can be large differences in the predicted value at a future date. Now this is called the butterfly effect in the theory of chaos. So there is a need then to take into account the uncertainty in at least the initial measurements, if not in describing the dynamics of the system. Now it's in the middle of the 19th century that systematic effort is made to explain the concept of variation, or to explain, to describe uncertainty rather than to explain uncertainty. Now Adolf Hitler, he tried to study social and biological phenomena. I believe he fitted about maybe 2,000 normal curves to the various kinds of data he had on social and biological phenomena. Then came George Mendel, who tried to explain the hereditary mechanism through chance. Then finally, in the hard science like physics, they tried to explain formulate the laws, the physical laws, in terms of a random movement of the fundamental particles. And that led to Boltzmann first introduced the probabilistic interpretation of the second law of thermodynamics, which led to the development of modern quantum mechanics. Let's see how new knowledge is created. Of course, these are various logical processes which we employ in any investigation. First, of course, we have deduction. As I mentioned, that is a process by which we argue from given premises. So we are not creating, in some sense, any new knowledge, because all knowledge is contained in the axioms to begin with. Now, it's induction which is important for us, where we are trying to create new knowledge based on observational data. Now, there's a strong team of workers who work in artificial intelligence, who believe that all scientific discoveries can be made by properly feeding the available data into the computers. Now, the chief proponent of that is Herbert Simon, the Nobel laureate. So he says that scientific discovery, however revolutionary it may be, comes within the normal problem-solving process and does not involve mythical elements such as creative spark, flash of genius, or sudden insight. Problem finding, identification of relevant data, and selective search guided by heuristics, which are major ingredients of creativity, are programmable on a computer. In this book, they have given examples to show how, by using the knowledge available at any point of time and the observations that are available at the time, we could have discovered all the laws which have been discovered in the past. For instance, they show how, with the data, by feeding them into a computer, they could have discovered gravity. So they give examples of all the past discoveries and show how they could have been obtained through the normal process of feeding data into a computer. So if I end up by saying, we would like to imagine that great discoverers would be pleased with this interpretation of their activity as normal human thinking. So any one of us today can come out with a big discovery by laying our hands on the available data, using a suitable program, and using a good computer. Now, science is concerned with the way the world is, not how we would like it to be. So we must continue to try new experiments to be guided by new evidence in a heuristic search that is never finished, but it's always fascinating. Now, it may be interesting to know what Einstein has said. Pure logical thinking cannot yield us knowledge of the empirical world. All knowledge of reality starts from experience and ends with it. Decisions arrived at by purely logical means are completely empty of reality. I thought Einstein would not have said that, but he actually said so. We have another logical process called induction. This is creating new knowledge by intuition. This is what is meant by saying propositions arrived at not by logical means, by a flash of genius, something occurs to us and turns out to be something nice for explaining natural phenomena. It's without any observational basis. There are some people who think that all new discoveries are made through abduction but not by induction. That's at some stage there must be some little spark in our mind which comes out with new ideas. Now, the proponent of that is Roger Penrose. He says, he does not say anything nice about computers in his book, The Emperor's New Mind. This is a new book which came out this year. The very fact that the mind leads us to truths that are computable convinces me that a computer can never duplicate the mind. So in his book, he says that all new discoveries arise from a spark of imagination. That's all by abduction, but not by induction. Now finally we have random search. You create new knowledge by random moves. Now the proponent of this is Radhakrishna. He is the director of the only random search laboratory in the world, which is in Moscow. Now he has written a very nice book called The Chancy World, where he describes how you can exploit randomness and uncertainty to create new knowledge. If, for instance, you want to create a gadget to perform certain functions, what you can do is to adjust the levels of certain factors which go into the gadget at specified levels for certain factors about which you have some knowledge. But with respect to the other factors, you leave the gadgets to choose at random and then observe how it performs. Now when you find that it is performing in a nice way, then you go and see what the levels of the various factors are which produce that kind of performance. So you discover a new combination of factors which optimize production. So this is a book, and it's a very thriving institute in Moscow. The fundamental equation on which statistics is based is the following: that no doubt that the knowledge we create from observational data is uncertain, but if we know the amount of uncertainty in the inference we are making, that constitutes certain knowledge. It's the logical equation on which the science of statistics is founded. So the key to wise decision making is then quantification of uncertainty. So if by various rules we have we try to create knowledge, but corresponding to each rule there is a certain amount of uncertainty in the knowledge we create. So the best rule is then which minimizes the amount of uncertainty in our conclusions. So that's the optimization problem. This is what we have been trying to do in statistics when we maximize the power or minimize the variance or minimize the loss function. Now the first fruits of this concept of quantifying uncertainty is the way the weather forecasts are made nowadays. Some years ago, the weather forecasts used to be as definite statements: it will rain tomorrow or it will not rain tomorrow. Now when the weatherman says it will not rain tomorrow, nobody would carry an umbrella when they go out. When he says it will rain tomorrow, everybody will carry the umbrella. But yesterday, while looking through my window of the hotel, I found only 1% of the people were carrying umbrellas, and it was slightly drizzling. Now such decisions are based upon the information given to us by the weatherman in a slightly different way. Nowadays they say it will rain tomorrow with a chance of 30%. Now don't think it's a non-committal statement by the weatherman, because if it rained, he would say, yes, I said 30% chance. If it did not rain, he said, I said only 30% chance of rain tomorrow. It's not a non-committal statement, but if you come to think of it, it's the most scientific way of conveying information to us that in the past, when the weather conditions were as obtained today, it would rain 30% of the times next day. And it's up to you, based on this chance, to carry an umbrella or not. So the most scientific way of conveying information to us is essentially in the following way: at the chance of a certain event happening, but not to assert whether a certain event will happen or not. Now coming to quantification of uncertainty, this is where one could spend hours and hours discussing what is the best way of quantifying uncertainty. Of course, we have the base rule, which is probably a nice way of quantifying uncertainty, but there are some. After Bayes came out with his theorem, the classical the founders of statistics found that it is not an acceptable rule. They tried to develop they tried to introduce various methods of quantifying uncertainty. I think the first attempt was Carl Pearson, who used the concept of standard error. So when we make an estimate, you would see in all the papers it is theta some like 25.2 plus minus 2.3. So this is a kind of standard error which tells us that the true value is likely to be in a particular interval. Then came Neyman and E.S. Pearson, who introduced the formal theory of testing of hypotheses and confidence intervals. Then, of course, R.A. Fisher was responsible for introducing the concepts of likelihood, fiducial inference, estimation, and level of significance. So some of them are logical concepts, and some of them have found to be not consistent procedures. So they have been given up. Now recently, during the last 15 years or so, we have lots of theories aimed at quantification of uncertainty. One is the Dempster-Schaefer, which is an extension of the Bayes rule, and a fuzzy set theory, and Mycene method, which is popular among medical people, a Cohen system of inductive probabilities, and non-monotonic reasoning methods. There is no systematic account of all these methods described, but one has to read a number of papers. Well, I am not sure. I have spent a lot of time reading these papers. Some of them are not easy to understand. Probably some of them will be given up and some will be pursued. I will by giving you some examples which I like most as application of statistics, as how statistics can be useful in taking certain decisions. Now this is an example taken from a paper by two Stanford statisticians, Thisted and Efron. This is some years back, Taylor, a Shakespearean scholar, he discovered a poem. The time at which the poem was written is known approximately at the time of Shakespeare, and it is not known who wrote the poem, whether Shakespeare himself or one of the contemporary authors. Now, how do we decide about the authorship of this poem? In order to do that, these two statisticians made a certain analysis of Shakespearean works. It appears that the total number of words in all works of Shakespeare is of the order of 884,647. And Shakespeare used only 31,000 distinct words in all his writings. And the distribution of the words he used is the following. The 14,000 words he used only once in all his writing. About 4,000 words he used only twice. And about 2,000 words he used 3 times. You see how you can make an analysis of your own writings this way. Take the number of distinct words he used, and you might have used one word number of times, another word a smaller number of times. So this is the distribution of works of Shakespeare. Now there is, of course, Shakespeare might not have used some words which he knew. That's quite possible. We know many words, but we may not use them in our writings. So how do we estimate, in order to know the total vocabulary of Shakespeare, we must be able to estimate the number of words which he knew but which he did not use. Now there is a famous distribution introduced by R.A. Fisher which does this, which estimates this for us. It was actually introduced by Fisher in order to estimate the number of species of butterflies. The number of distinct species of butterflies is not necessarily equal to the number of species which we catch, but there are some species which we might not have come into our net. So we should be able to know how many species were not caught. So using that information, that distribution, it was estimated that Shakespeare probably knew 35,000 additional words which he did not use in his writings. So the total vocabulary of Shakespeare is at least 66,000 words. At the time of Shakespeare, I believe there were only 100,000 words in the English language. Now we have 500,000 words, including standard error and things like that. Oh, now, how is this information used in deciding whether the new poem was written by Shakespeare or by one of the contemporary authors? Now, this is how the further analysis was undertaken. The new poem had 258 distinct words, and the total number of words is 429. Now, there were 9 words in that language which Shakespeare did not use before. There were 7 words which Shakespeare used once before, 5 words which Shakespeare used twice before, and so on. Now, if Shakespeare were to be the author of this poem, we would have these are the expected values of the corresponding numbers. Then Shakespeare would have used about 7 words which he did not use before, about 4 words which he used once before, and so on. Now, you take poems of equivalent length written by other authors like John Donne, Christopher Marlowe, Ben Jonson, who are contemporaries of Shakespeare, and an analysis of their writings gives this kind of distributions. So we see from this that there's a greater likelihood if these 2 columns are close together, which suggests that probably Shakespeare was the author of this new poem. I would like to give one more example which I like very much. This is something which happened in, I think, Sweden or Norway. This is the biologist in 1900. He's an ichthyologist. He studies fish. Now he found this interesting phenomena. The eels caught in 3 different regions, like Iceland, Azores, and Nile, which are thousands of miles apart. And he found the distribution of the fins of the eels caught from these 3 areas. And he found that the distributions were similar, although the eels were caught at regions separated by thousands of miles. Whereas the same species of fish caught from 3 different regions in a lake, where the regions are not far apart, maybe less than 100 miles. Now they show differences in the distribution of the fins. So how could this happen? Now he came out with a beautiful conjecture. He said that all eels are bred or spawned at one spot, somewhere in the Atlantic, and they migrate to distant regions. So if this happens, we should expect that the samples of eels caught from these different regions, they look similar. Now notice that in 1900, by just looking at the figures, he was able to speak with the figures, and they told him that yes, the eels must be spawned at one particular spot in the Atlantic. And that was his conjecture. And in fact, it was confirmed in 1963 when the research vessel Dana discovered the breeding ground somewhere in the Western Atlantic of all the eels. So you see how powerful the statistical approach to the problem is. By just arranging or organizing the observations we have, we could extract information of very great consequence. Since I'm running out of time, I skipped the other examples, and I would like to leave with you this thought that statistics is more a way of thinking or reasoning than a bunch of prescriptions for beating data to elicit answers. So you may acquire all knowledge of methodology, which we'll listen during the next 3 days. But please remember, but these are not going to lead you to final conclusions. That this is what is called statistical thinking, which should follow all the methodology which would apply to reduce the data. Now, life is the art of sufficient conclusions from insufficient evidence, and through the development of statistics, we are able to say that decision making is no longer a gamble with an unpredictable chance of success or a hit and miss affair. It is now within the realm of scientific techniques whereby optimal decisions can be taken on the basis of available evidence and results monitored for feedback and improvement. Finally, remember that, sorry, I don't have the transparency, but it says, to guess is cheap, to guess wrongly is expensive. This is an old Chinese proverb. Thank you very much.